Hello everybody and welcome back to my channel. Today we're going to talk about our progress so far on the HoverGames 2 competition for NXP. This competition tasked us with coming up with an idea on how we can help people using drones during a pandemic. Our solution for that was to create a drone using machine learning, specifically reinforcement learning, and computer vision to keep animals, wild animals, out of a keep-away zone. That keep-away zone specifically being a rancher's field or a farmer's crops. To do this, our base station, which we will have running on the ground, will be using computer vision to sense animals in a field. It will then trigger the aircraft to take off and chase the animal out of the field. To do that, we classify every frame that comes in. We look for the animal, or in our case we're going to use humans as stand-ins. We look for the humans, sense the human, track the human frame to frame, and then that position in the field goes into a reinforcement learning algorithm which has been trained to defend against emergent swarm behavior. And what it does is it optimizes for the correct position of the drone to be commanded such that when the drone gets to that position it will scare away the animal or human. So when the classifier senses a human, it puts the human in the scene. The reinforcement learning is then ran over the scene and a position is generated that the drone should go to. When the reinforcement learning algorithm decides that the drone needs to move, it will send a message to the base station. The base station will authenticate that message and make sure it's coming from the proper source before passing it on to one of its known drones that it controls. It will trigger the drone to then take off and travel to that point in space, effectively scaring away the subject in the image. Once the reinforcement algorithm decides that the drone no longer needs to be in that position, it will command the drone to return back, at which point the drone will return back to home and land, and we will have a simulated docking event where the drone can recharge and prepare itself for the next intrusion. To make this a success, we need very good, accurate positioning. Our solution for that, for now, is to use some off-the-shelf parts, such as the PX4 Flow, which you can't really see, but if I do this here, PX4 Flow, and the LiDAR light. What this allows us to do is have GPS denied or non-GPS position hold. The flow sensor measures the features on the ground and is able to sense how far the drone has moved laterally, and the LiDAR gives it a sense of depth from the ground. Those three dimensions allow the drone to be able to accurately hold itself in space at a specific point, which means that when we command a position to the drone, we're not dealing with the inaccuracies of GPS, but rather the accuracies of the flow sensor and the LiDAR in small ranges. You'll notice we still have a GPS on board, and that'll be used just for global positioning. But really the local positioning will take advantage of the LiDAR and the flow sensor that we have installed on the front of the drone here. In addition to the components we added to this drone, we have the components that came with the kit, which include the NavQ board, the Coral camera, the PX4 flight controller, as well as the miscellaneous parts on the drone to actually make the thing fly. We've decided to go with some Turnigy batteries, as well as using the standard remote that comes with the kit. So that's a brief hardware overview of our platform that we'll be flying for this competition. Let's hop into the computer and take a look at the software. First, we're going to look at a high-level overview of the components used in our software system. Then we'll jump in and see a demo of the Python interface, which runs alongside the reinforcement learning algorithm, piping messages over to the C++ interface on the base station, which then will eventually trigger the base station to send messages to the autopilot via Wi-Fi. Currently we have the base station and the Python interface code written. The reinforcement learning and the classifier are 75% done. They just need a little more training time. And the onboard software has yet to be written, but the infrastructure is pretty much there, given it will essentially be a different flavor of how the base station was written. we'll get more into that when we look at the code. So let's go ahead and hop over there and I'll let you see everything we got so far. To start off, I'd like to first go over our Docker file. That way you have an understanding of our development environment. Then we will actually run the Docker file into a Docker container. We'll hop into CLine and then we'll look at the code and I'll show you the various pieces and how they all connect. So for starters, the Docker file. Here you can see we have a Docker file that's Ubuntu 18.04 flavor. This allows us to control the various different packages that we may need, as well as any types of configurations that we need to be able to build the project on any device. You'll notice I'm running a Windows computer, and the NavQ board is actually in Linux, as well as our base station board is in Linux. So we need to be able to target Linux, but we need to be able to develop on the Windows computer. So what this allows us to do is actually run a Linux Docker container, connect into it, and then build all of our code and execute all of our code inside of it such that our code runs within a Linux environment. So it's really just as simple as running this command and waiting for the prompt to open up. Each time it rebuilds the container just to make sure that no changes have been made. That way, as we need to add new libraries, I can simply just add it, rerun the command, and I have a new image or a new container built for me. So once the container is built, I can run my CLine command, and that puts me into the CLine application using the xming program on Windows. Okay, so here you can see our code folder within our HoverGames 2 repository on my GitHub. For starters, we have a main CPP. It essentially will allow us to switch between the base mode and the agent mode. So in base mode, it's running as the base station. In agent mode, it's running as the drone. It will be running on the drone. The reason we did it this way was such that we could use the messaging library in both places, as well as the base UDP communications socket library in both places. That way, the only thing we really have to customize is the logic that lives on the base station and the logic that lives in the drone. Everything else is shared. So inside of our source folder, you can see we have a messaging folder, a utils folder, and a system folder. And we'll go ahead and go over them in that order. Inside of the messaging folder, we have messages. Messages are pretty simple. We have a set of common messages. And for starters, we'll start with the hello message. This is the message that gets sent from any node that's connecting to the base station when it starts up. One example of a node would be the controller, which is where our reinforcement learning algorithm runs within our Python environment. And all the hello messages is just a struct that contains certain variables that are needed to be able to set up communications between the base station and the Python interface. I won't go over all the messages. You can go ahead and go to our GitHub and look at those messages to see the various flavors that we have, but I will go over these three classes that lie beneath the messages folder. The base class is the communicator. It allows us to do things such as registering callbacks for when messages come in. We can use the callback to actually process the message. Sending acknowledgements, so when we get a message and we want to ACK that we got that message, we can send that acknowledgement message by just calling send ACK. It also reserves details of who we contact. That way we don't have to actually tell it who to send the message to, other than just by using the target ID, which is our node ID if you're looking at the messages. It also has helpers for filling a header and sending just a raw message. The drone communicator will add on top of the communicator, similar to how the base station communicator adds on top of it. Again, we haven't really done much of the drone code yet, but we do have the base station code, so you can get an idea of what the drone code will look like. So the base station code has things like send welcome, forward agent location, forward subject location, and send agent move command. The base station is responsible for forwarding these two locations as well as sending a welcome when a hello comes in, and it's responsible for sending the agent, the drone, a move command. So you can see these are the messages that the base station is able to send. Inside of the utils folder, we have the Mav SDK, which we'll be using on the agent or drone side of things to be able to contact the PX4 autopilot, and we have a thread pool library that allows us to actually set up a thread pool such that we can call down to each of the handlers that gets registered via either the base station system code or the agent system code. Now, I've mentioned the system code that lives inside of the system folder. So think of this as like the really main area where the logic is held. Again, our agent we haven't written much of. It implements the runnable interface, which is just a class that I built that allows us to have a single thread that just runs at some rate. Prior to that thread being run, you get called doSetup, and after the thread exits, you get a doStop. So you have a start and a stop signal. Inside of the controller code, we have the Python. We'll get into that in a second after we look at the base station. So the base station consists of the base station.h and .cpp. And again, it implements a runnable interface. So we have one run thread that allows us to do something at a defined rate. And then we have the various handlers, which are our callbacks for the different messages that the base station is able to receive and react to. So we handle new node, which is handling the hello message, as you can see. We have the ACK, so if we ever get an ACK, we can handle it there. If we ever get an agent location, we can handle it there. Subject location, agent move command, etc. In addition to those, we have the two helper functions that are isAgent and isController. And all these helper functions do is essentially search a map, which is here, of active agents and active controllers, and it just allows us to make sure that when someone sends a message with a certain ID, that we know that they're able to send that message based on the rules of what controllers can do and what agents can do. So really the base station is the rule enforcer. Lastly, we have the agent owner map, and this basically just maps the owner, which is a controller, to an agent. When a controller joins the network and when an agent joins the network, they register themselves, and then the base station hands out control over the agent to the controllers. So the base station understands who's allowed to control certain agents, and so every time a agent move command is received at the base station from a controller, the base station checks against its map and then either approves or disapproves of that message and either forwards it or doesn't forward it and sends a NAC message to let the controller know that it's not allowed to actually control that agent. So I could get in and walk through the various pieces of code. I'll do a light overview of everything, but essentially we have our register callbacks for our various handlers, and so the communicator.register callback, very simple interface to register callbacks, and all that does is it sets up these messages down here, or these functions down here, to be able to handle messages as they come into the system. So basically every one of these handlers casts to the message it needs, and then it's able to, at that point, pull the various items out of that message and make decisions based on them. So when it gets a hello message, it can eventually send a welcome message, which gives the node or the controller/agent their information they need to be able to operate. It can handle ACKs, which for now just prints out some stuff, and it can do all the various other things that I talked about in the header file. So with that being said, we're going to go ahead and jump into the controller code next, which is actually just Python code. So the reason why we went with Python code for the controller was because Adam finds it much easier, as do many people, to develop machine learning within Python because it's a much easier environment to write code in. And the libraries seem to be probably more up to date in terms of machine learning because it's more of a data scientist friendly tool versus C++ being more of a programmer friendly tool. So all of our classifier and reinforcement learning is run in C++, but we're using libraries, or sorry, it's run in Python, but it's utilizing libraries like Torch and things like that that actually do use C++ under the hood, so it's still fast enough. So following a similar structure, we have a messaging folder inside of our Python folder for our controller. The messaging folder, again, has a folder of messages, and all we've done is essentially created an interface for the various messages and given functions just to help with grabbing the data out of that message. Inside of the init, you can actually see some helper functions as well as the definition of the messages and then the struct string that allows us to parse the raw bytes that we receive off the UDP socket into the actual struct of the message. Down here we have the base class message, which essentially you give it the raw bytes and it parses out the header and allows you to then parse out the rest of the code or the rest of the packet as a child class. An example of a child class would be like agent location, hello, welcome, or ACK, as you see on the left hand side here. So that's the messages. Next up we have a helper function called parser, and all this does is basically takes raw bytes and then builds a message based on the first byte being the message ID. So if we go all the way back to a message, we'll see every message starts with the header, and if we go to the header, we'll notice that every header starts with the message ID. So that way we can click on, or we can rather pull out the first byte of any message, and that'll tell us the message ID. We can then use that to parse and figure out what message we need to construct from that set of bytes. So now we get down to the controller interface. This is essentially the main code of the Python interface. At the top we have two helper classes. One's called subject and one's called agent. Those are, as you would expect, the subject is the person in the scene or the animal in the scene, and the agent is the drone in the scene. The agent is a child of subject because they can kind of be thought of as the same. They have a location, they have a target location. Down towards the bottom we have the controller interface. This is the thing that Adam will be using from his end to actually get his code connected into our system. So all he'll have to do is create a object of the controller interface, pass it the IP address and the port, if he needs to. Otherwise these just remain as they are, and it works with the C++ code as written currently. The controller interface has a set of private variables as denoted by this underscore in the front of the letters. It has a couple public functions like start, shutdown, register new agent location callback, and register ownership change callback. So start will actually turn on the main thread that listens for UDP packets, and then it'll also tell it to connect to the base. So if we hop down to connect to the base, what that does is essentially we'll create a hello message and then send it to the base station, or what it thinks is the base station. And it'll continually do that until it's received an ID, which means that it's received a welcome message, because the welcome message is where you get your ID from. It has a get agents function, get my agents function, get subjects, and add new subject function. Then down low we have a listener function, which essentially is the thread that runs to be able to just pick messages off of the UDP, to receive messages from the UDP socket. And then essentially what it does is every time it gets a message, it calls on new message, it decodes the message, which we saw earlier in the parser folder file. And then once it decodes the message, it's then able to handle the message, which essentially looks just like the base station, where if it's a welcome, it's going to do certain things. If it's an agent location, it'll do certain things. And so basically all this interface does is it receives agent locations and puts them into the various lists that this class has access to, and that the user of this interface has access to. In the future, when we have multiple base stations and multiple agents, we're going to also be handling subject locations, because we'll have other base stations creating subject locations. But for now, we're just working with one base station to keep it simple. So that's pretty much it as far as the code goes that I've written. I'm going to go ahead now and kick it over to Adam, and Adam will show you the Python code he's written for the classifier as well as the reinforcement learning interface. So go ahead, take it over, Adam.
So as Ian mentioned, I'm working on two components of this project. The primary component being the reinforcement learner, and then another component being the classifier for the animals, which in this case we're using humans as surrogates for testing purposes. It's a lot easier to have humans do what you want them to do so you can get a good test than to just go out and try to find animals. We will also do further tests in the future, actually working with wild animals, just to make sure that it actually works in practice. So for the classifier piece, there's a lot of classifiers out there for wild animals. There's different kinds of conservation efforts going on, and there's a lot of data sets and even trained classifiers out there already. So we could maybe leverage that to sort of start things, and then we could eventually collect our own data by actually capturing in the field video of feral hogs or wild animals that are causing destruction to protected areas. So one of the things that I'm doing right now is we're using humans as surrogates. It's a lot easier to have humans do something that you want them to than expecting wild animals to give you a good test. And so later on, we'll actually convert to using wild animals just to make sure it actually works in practice as well for the end goal. But to start, we're going to practice with humans because we can kind of direct them to walk into the keep out zone and make sure the drone behaves accordingly. So for the classifier piece, we're using a Jetson Nano. I'm just using an off-the-shelf person detection algorithm for that. That's a pretty straightforward thing. There's a lot of stuff out there that's readily available and easy to use. So just getting that spun up so that I can do inference on the Jetson Nano. There's Raspberry Pi cameras that are used for the camera system, and then all the inference compute is happening on the Jetson Nano. As far as the reinforcement learning piece goes, I've been working on a SCAREcrow gym environment. And so OpenAI has developed kind of this framework for reinforcement learning that's pretty commonly used in academia and video game industry, kind of everywhere to sort of play around with reinforcement learning. And so what I did is I leveraged some of that work that's been done there to use their kind of framework and architecture. And I created what's called Gym SCAREcrow. So it's a gym environment that's based on our SCAREcrow problem that we're solving here, or our SCAREcrow solution to the HoverGames 2 problem. So there's kind of three primary things that come with reinforcement learning. There's an observation space. So that's what your agent can actually see about the world that it's working in. And then there's an action space. So based on what it sees, what is it going to do? So that action space is what the agent actually does to interact with the world. And then there's a reward structure. So to get your agent to do things you want it to do, you provide a reward. So it's like you can give a penalty for it to learn not to do something, or you can give it a small reward for doing something that you want to encourage it to do. And then overall, it sort of learns its own policy that most effectively solves the problem. And so the nice thing about this is that you can really have the agent learn and do the exploration of trying to figure out what's good and what's not, and you don't have to. So one of the things I think with this problem that makes reinforcement learning desirable is you have sort of these erratic behavior or emergent swarm behavior, or there's all kinds of different things people call wild animal behavior, and how they kind of congregate together, and some break off and do other things. And so it's not very well understood or well modeled, especially for feral pigs. And so one of the things that we're interested in doing is having the reinforcement learning agent actually explore the best way to herd these animals out of the keep out zone and protect the keep out zone. And so I guess we could sit around and explore that space forever and find a policy that works well. But if we can just have an agent spin up and kind of do it while we're doing other things, that's a much more useful way of time. And they may even find some exploits that are even better than we could come up with. So for the observation space, we kind of have 7 different types of, representations of each grid in our grid space. So all of the red dots and the blue dot there, they're moving in continuous time, but I'm quantizing them in this grid space of this known kind of game board area, right? So in each of those grids, there's a value that can be taken between 0 and 7. So a value of 0 would be an open green space, so it's just open field. A value of 1 would be that blue dot, which is our agent, which is our multi-rotor that's flying around. And then we have a red dot that represents the threat, so that could be, or a subject. So that subject could be a wild animal, it could be a person, whatever it may be. And then we have the third representation, a third value for one of these grids could be a black X. And so the black X is any of the green squares that there's nothing occupying them inside of this red box. So that red box is normally black, which you'll see in a video I'm about to show in a little bit. But when it gets breached, it highlights red just to notify that there's been a breach. And then the fourth representation could be a black and blue. So that means that it's a blue agent inside of a empty area within the protected keep out zone box there. And so that blue dot right now, as you're seeing in that green game board layout, would be a black and blue if there was not that yellow dot next to it, which I'll get into here in a second. So then the fifth representation is black and red. So black and red would represent a breach. So it would be that red dot inside of the red square there on the right-hand side of the red square. So that means that it's within the boundary, the keep out zone, which is normally black. But since it's breached, it turned red. And now that agent has breached the safe zone or the keep out zone. And then there's a sixth value that can be held, which is blue and red. And so blue and red means that there was a spook. And so when a blue agent gets close to a red agent, that red agent turns yellow, highlighting that it's been scared. And then it will have a repulsive force away from that blue agent because it wants to get away. And then there's a seventh value that the observation space can hold, which is a black, blue, and red. This is basically that blue dot and that yellow dot inside the box right now. So the blue agent is spooking the red agent, it's turning yellow, and it's within the black square, which is red right now because it's breached. And so that's what our observation space looks like. As far as action space goes, there's 4 actions that the agent can take. It can take an action of forward, an action of backward, an action of right, and an action of left. And so we started out initially kind of looking at the continuous space for this. So giving it a velocity vector and a direction. And so the difficulty there is that's a really kind of unstable thing to learn to make sure it's transferable to real world. So we wanted this agent to be able to be trained up in this simulation environment. And then we want to be able to transfer it to the actual live drone. And the way that we have this set up right now is we can actually represent our real world space this way. So we take the camera footage, get the positions of the different subjects. We know the position of our agent. We know the geofence for the keep out zone. And so we can make the same representation of the real world, which is really valuable. The difficulty becomes is the dynamics of the UAV are really hard to properly model in this game environment. And the reinforcement learning agent will certainly learn some traits like that. So we want to make sure we mitigate that as much as possible. So by doing forward, backward, right, left at a fixed distance for each movement, was a much more effective way to make this as transferable as possible to the real world. For a reward structure, basically what we're doing is every time a subject breaches the keep out zone, we're giving a big penalty of 10. And so what that penalty does is it encourages the agent to not let things inside the breach zone. And then we're also looking at what we want to do to encourage it to actually spook things and keep them away. And so this is a really hard thing. I think the reward structure is one of the most difficult things to set up in a reinforcement learning problem because this is how you're telling the agent whether they're doing good or bad. This is your feedback signal. And so the agent can find ways to get the highest feedback signal, but actually not solve the problem you want them to solve. So you have to be really careful with the way you build this. And so one of the hardest parts was, well, how do we encourage it to spook things and drive them out? And not at the same time encourage it to just run around and spook things really far away from the keep out zone and just basically build up a bunch of points for spooking things outside of the keep out zone. So one of the ways that I'm trying to do that, and this will be iterative, I'm sure we'll change the reward structure as we go, but my initial thought process was we give it a +1, so it's smaller than the -10 penalty, but we give it a +1 for spooking something multiplied by a normalized distance away from the keep out zone. So this will encourage it to spook things closer to the keep out zone rather than just going off into a far off corner of the game board and continually spooking something just to build up points. And so that's one of the ways I'm trying to mitigate that and kind of encourage it to stay near the keep out zone and protect it while also trying to spook things and drive them out of the keep out zone. And then those subjects, those little red subjects, which were our end goal is kind of to protect against wild boar tearing up property and farmland. is that we're trying to model their behavior in a somewhat representative way. So right now I'm using a Boyd's algorithm, which is just a common flocking behavior algorithm for a lot of like emergent swarm type behavior. I'm also curious in looking into potential fields, which is another method that's used for doing this kind of behavior modeling of animals. And so I think that that's a good place to start. It's obviously not ideal. It may not be exactly how wild boar move or other wild animals. But one of the things I think is kind of cool is we can update that behavior model as we go and make it better. So once we collect enough data of like actual live boar footage that we're collecting, then maybe we can get a better idea to create a better model of what their actual behavior is like. So that's something that may come in the future. Okay, now I'm going to go through a quick video of the environment just to kind of show you how it works. It's not completely there yet. I'm still working on it. It should be wrapped up pretty shortly. And then we can really start training and sort of like tuning this reinforcement learning agent's reward structure and possibly even some of the other feature spaces. That way we can get better performance out of it and make it more transferable to the real world. So here I have a video. This is my code base right now as it stands, and I'll kind of walk through sort of what's happening here. So I have this gym environment. You basically spin up and run the gym environment. It's run with a reinforcement learning agent kind of on the outside of that wrapper. So what's happening here is I have these agents, these subjects are moving around in the environment pretty randomly. So they're placed on the board randomly. You can choose how many subjects you want. You can choose how many agents you want or how many multi-rotors you want, which the multi-rotors are these blue dots, and then the subjects are these red dots. And so the way it's set up is I have this whole framework set up that it can be completely multi-agent with multiple blue agents, as well as you can choose in your params file how many subjects you want, how many of these red dots you actually want to show up in the training scenario. And as I train this, I will modify the size and shape of this keep out zone, and I'll modify the number of threats or the number of subjects and the number of agents. So that way you can learn like a pretty general policy across all these things, or that's the hope anyway. We'll see. So what's happening here is these things are kind of flowing across the screen. I don't have the Boyd's algorithm fully worked out yet. I'm really close to finishing that up. But what they're doing right now is they're just kind of flowing across the screen, and eventually their steering vectors or their velocity vectors will steer towards a leader in the group. And they'll do a little more swarm-like behavior. And then they'll be attracted towards the center of this keep-out zone. And they'll have a repulsive force. They'll be attracted to each other, attracted to the keep-out zone, and they'll have a repulsive force from the agent, which is our multi-rotor. Now, they want to kind of follow each other, but there is a probability that they break off as well. So not always will they follow the swarm. They may break off and do something different or form even a second swarm if others start to break off and they start to come back to each other again with that attraction. Now, here you're also seeing that the space is breached. So here's the keep out zone. That keep out zone is breached because these subjects have entered this black square that's now highlighted red because it's been breached. And so that's like one of the things that you'll get a -10 penalty here and a -10 penalty here at each time step for them breaching this keep out zone, which is the ultimate thing that we're trying to protect against. Now, if I continue, you'll sort of see right now this agent's not trained either. So after I kind of work out all of the other simulation details, then this agent will start to get trained up. But right now the agent's just moving randomly, completely random. But as the subjects leave the keep out zone, it turns black and the breach label disappears. So this guy's on his way out, and that's recognized. I've actually updated the code for this to be a little bit different. So before it was, if it noticed it was leaving, it stopped counting it as breached. But I do have also a code version that keeps it breached the whole time. As we start to train and kind of test things and see what our performance results look like, I may or may not keep that feature in. I'm not quite sure yet. But as of right now, if the velocity vector is heading on its way out, then that breached signal disappears. And then you'll see what was happening there is as the agent gets close to as the agent gets close to the subject, then it's spooked. So it gives the spook signal, and then the agent is close enough to that, it's within the same grid pattern, that it's scaring that that subject. And now, as I start to get more of the behavior logic in, that behavior will be that this subject is scared from this agent, so it'll turn with a velocity vector completely opposite of the agent, so along this direction. And that will help drive the subjects to a different area. So the idea is that this agent can eventually learn the most effective way to fly at these subjects in order to drive them away from the keep out zone. Another thing is for the reward structure, here for the spook, you're getting a +1 for the spook times a normalized distance from the keep out zone. So you'd have a normalized distance here between 0 and 1, and that would be the amount of positive reinforcement that you get in that reward signal for actually spooking this agent, and then doing that normalized distance multiplication there to give you a value between 0 and 1 just forces the agent to try and stay close to the keep out zone and protect it rather than just going off in a corner over here. So like for instance, in this case, the agent could, if I just gave it a reward for spooking the agent, it could have just came over here and spooked this agent as all these agents are kind of flying away from the keep out zone. It could have just continued to spook this agent a bunch to get up a bunch of points to basically gain a bunch of rewards in that reward signal. And we don't want that behavior to happen. We want it to stay sort of close to the keep out zone and make sure the keep out zone stays protected. So that was the reason for doing the +1 for the spook multiplied by a normalized distance from the keep out zone to give you a value between 0 and 1, just to try to keep the agent around this keep out zone. And then basically this scenario plays out until all of the agents are out of the screen or all the subjects are away from the screen, and then we'll just assume that the agent is returning to land because it doesn't see any more subjects, or those subjects could re-enter the screen again and it can continue to play out the scenario as it goes. And so this is sort of an infinite horizon problem. There's no real end to the game. So we'll just train and train and train until we start seeing a good policy being formed. And then we'll just decide to stop kind of when we start seeing good behavior coming out of it, and the reward will start to kind of trail off and level off. And so that's where we're at. We're really looking for awesome results. I think things are working really well and we have a good path forward. So I'm really excited to see where things end up. Now I'll send it back to Ian.
We hope you've enjoyed our overview of our current progress up to now on the HoverGames 2 competition. Today's date is December 12th, 2020. We plan to, in the next few months, have the RL hammered out and potentially do a test flight. We have a small amount of tuning left to do to get the position hold of the PX4 flow accurate enough to be able to actually do a test flight in my backyard. But once we have that figured out, we can do a test flight and make a cool video of the whole system working properly. If we are unable to do the test flight, we will have simulations of the code on the ground in the reinforcement learning algorithm talking to the base station, and the base station sending commands to the drone, and then we'll have a basic simulator in the drone that basically just takes the commanded position and steps through time towards that position to emulate the drone movement back down to the ground station and through the ground control station over to the reinforcement learning algorithm, such that the reinforcement learning algorithm thinks it's actually controlling a real drone. Hopefully we're able to do a real test, but if we can't, we'll be able to at least prove the concept with a simulated drone doing the test. So thanks for watching. If you want to see more updates, go ahead and hit that subscribe button down below, like this video, and if you have any questions, go ahead and comment. Also make sure to follow my Instagram page, Logically Literate, over there on Instagram. I'll also have a link down below for that. Also, you can find all the code that we're creating for this project on our GitHub pages. If you navigate to github.com/mcelhenny, that's me. You'll be able to find the NXPHoverGames project there. I will also have a link below for that project. In addition to that, that link to that project, GitHub, will link you over to our reinforcement learning GitHub on Adam's page, where you'll be able to see all the reinforcement learning and classification code in his repository. So thanks for watching, and stick around for our next video. Thanks.